Okay, in this video I'm going to continue on with exercise 5C of the book Fundamental Applied Mathematics. We're on page number 139 and the question is 2. Now this is the first of these sorts of questions, and for that reason I'm going to go into a reasonable bit of detail. It reads: a block of mass 100 kilos is dragged up a smooth slope which makes an angle A with the horizontal, tan A being 4/3. If the pulling force is of magnitude 984 newtons and is parallel to the line of greatest slope, find the acceleration in the block. So, similar to our projectile questions, we always defined our xy plane, or our Cartesian plane, like so. And we worked out that when we started projecting things, it was often easier, up an incline, it was often easier to create a new xy plane. So we'd say the x-axis for the new plane is along the incline, and then we'd say the y-axis is perpendicular to that. And what we create is an x prime, y prime plane, and we know, of course, we're able to always get from one plane to the other because we know the difference in angle. So that was the best way to do it. And we used to have, if we're just dealing with our Cartesian plane, we define our unit vectors like so. However, if we are converting to a new plane, it's always better just to change the unit vectors. So we'll say that the unit vectors are in this direction and this direction, parallel to the x prime, y prime axes. So that's what we're going to do here. We're going to do that exact same thing. Alright? Now, because I don't want to mess up my diagram, you'll just have to know which is which yourself. So let's just sketch the motion. So I'm going to draw my incline first. There's my incline, and I'm going to call that my x prime axis. And perpendicular to it, of course, is my y prime axis. The next thing is we need to draw the horizontal, which is the x-axis, like so. And we know this angle here is equal to A. I suppose that doesn't look great there, does it? I suppose it looks better. The next thing we need to do is draw the block. And we're told the block is just a block, so it could be any shape. So I'm going to draw this kind of rectangular shape here. We're told its mass is equal to 100 kilograms. So now you've got to remember, from now on, we're dealing with everything on the x prime, y prime plane. All right. So yeah, that's just the way to think about that. Now, what other forces are there? Well, I'm just going to define my unit vectors here. So this is going to be I hat, and this here is going to be j hat. We know that the gravity vector is going in negative, it's going to be negative g like this, so it's going in the negative y direction, not the y prime. We're told that tan A is equal to 4/3, so if tan A is equal to 4/3, just do a bit of Pythagoras, you're going to find that cosine is equal to, that's 3, not a 5, excuse me, 4/3, so we're going to have a 3/5 for the cosine, and a sine of 4/5. Alright, so look, that's stuff that you're well able to do at this stage. What else? We're told that there is a pulling force, okay, a pulling force, and I'm going to say the pulling force is, well, it's along the horizontal, which we know the horizontal plane, if you can imagine. Alright, okay, what else? The pulling force is magnitude 984, and is parallel to the line of greatest slope, which is what we've drawn. And its magnitude, so P is equal to 984, like so. And that's going to be in the I hat direction. So its magnitude is in the I hat direction, or it's 984 the I hat direction. What else? We told, it's smooth. It's a smooth slope. So let's think about this. Essentially, this block is lying on the ground, and the ground, of course, being our x prime. So it has a normal vector, and I've said before the normal vector is always perpendicular to the ground, or to the whatever something is leaning or touching upon. So in this case, here's the normal vector, and it's n j hat, we'll say, like so. The weight vector, however, doesn't change. The weight is always pulling something towards the center of the earth, and the center of the earth is still in relation to the x-axis, not the x prime axis. So similar to our projectiles, we had to have gravity going this direction, like so, and it's going to be equal to mg. So we'll say 100 g, and it's going in that direction, we'll say, all right, because we're not using unit vectors at the moment. So similar to the projectile analysis, we need to resolve this weight vector into its basically new x prime y prime plane, or into its new x I hat and j hat unit vectors. So that's pretty straightforward. So we draw the two vectors which when added together create it. You draw perpendicular to the, or parallel to the j hat, parallel to the I hat. They're at right angles, and they're in these directions there. So this vector here is, we'll say, w sub j. I'll do that again. It's w sub y in the j hat direction. This one here is w sub x in the I hat direction. Alright. So just to explicitly write everything, and I'm only going to do this really for this particular question, we can say the pulling vector is equal to p sub x I hat plus p sub y j hat. And these actually should be primes in fairness now, I suppose, if we're going to be really correct. And we know that's going to be equal to 984 I hat plus 0 in the j hat direction. We know the acceleration vector, or we'll say the weight vector. Sorry, not the acceleration vector. The weight vector is going to be equal to w sub x prime in the I hat direction and w sub y in the j hat direction. We know that this vector is opposite to the j hat and this vector is opposite to the I hat, so they're both negative. Alright, that is correct, isn't it? Yeah, they're both negative. So is there anything else which we know? No, I think that's pretty much everything. So what else can we do here? Oh, we need to find out the angle here between. We have to find out this angle here. Now, I'm just going to remind you of something. This is the exact same as the projectile analysis. If you have two angles, so this angle, I'm going to draw angle A in red, and I'm going to draw a new angle in blue. So let's say this is the angle B. And if these angles intersect at a right angle, like they're doing there, then A is equal to B. So I could call this here B as well, if I wanted. Alright, they're the same angle. If they intersect at right angles, they are the same angle. So once again, if we apply that up here, we'll find that's what we have. We have W sub y prime is perpendicular to the x prime axis. So we can say that this angle here is also equal to A, like so. Alright, so as a result, we can say that W is equal to negative W times the sine of A in the I hat direction, negative W times the cosine of A in the j hat direction. Do you remember, of course, that sine is opposite the angle. Sine is opposite the angle, and cosine is adjacent. Alright, so let's just work out what that is. So let's say the weight vector is equal to minus 100g times the sine, and I said the sine was equal to 4 over 5, and that's the I hat direction. That's actually supposed to be a 4, believe it or not, and negative 100g times the cosine, or the cosine, which was 3 over 5, and that's in the j hat direction. Alright, so just finish that off then. We'll say the weight vector is equal to 20 times 4, 4 twos are 8, so it's negative 80g I hat, and it's going to be negative 60g j hat. Alright, like so. I'm just going to note that. Where am I going to note it? I'll just note it here, in fact. So we can say the weight vector is equal to negative 80g I hat, negative 60g j hat. Alright, so we're doing pretty well so far. Now I know I'm doing this quite slowly. I know that. I'm doing that on purpose. I want this to be very explicit for the first time we've done this question. So finally we're ready to begin doing our analysis. Okay, so we're going to apply Newton's second law. So Newton's second law says the sum of the force vectors is equal to the mass times the acceleration vector. So let's apply this to the I hat unit vector direction, or the x prime axis. Alright? So we're going to get the following. We're going to get 984 I hat. We need to take away from that the weight vector, which is 80, or we can say add the weight vector, but it's going to be 80g I hat, like so. Is equal to the mass, which was, what was the mass again? 100 kilos times the acceleration vector. and that's okay. It's going to be in the I hat direction as well. So let's just pull out the calculator. So we have 80 times, not 81, 80 times 9.81. We need to take that away from 984 and divide the whole thing by 100, and we get an answer of 1.992. So we can say that the acceleration A is approximately 2 I hat meters per second squared. That's correct. Alright, the acceleration is approximately 2 meters per second squared. That's pretty good. Now what about the y prime axis? What are we going to do there? Now we're told it's being pulled along the ground, so it is the force, of course, is only pulling it along the horizontal, we'll say, the new horizontal. So there is nothing pulling it into we'll say, the y prime dimension, or the j hat unit vector direction. So as a result, let's just do this. Let's do this quite explicitly. The sum of the forces around the yj is equal to the mass times the acceleration in the j. So what are the forces in the j hat direction? We have nj hat. We have negative 60 g j hat, because that's the weight vector, is equal to its mass, which is 100. Alright? And the question is this: is it accelerating? Is it moving in the j hat direction? And the answer is no, it's not. So its acceleration is 0. So you're going to get the normal vector is equal to 60g, is equal to the weight vector. Which is what you'd expect. When something isn't moving or accelerating in a certain direction, then all the forces are equal. And that's why when you're on the ground, for example, your weight vector is equal to the normal. Alright, so what else are we supposed to get here? Find the acceleration of the block, 2 meters per second squared. Alright, so the next part, of course, is if the slope was rough and the coefficient of friction was a third, find the new acceleration. Alright, so let's just be a bit smart about this, and I'm going to draw it in blue. So I'll take away A for the moment, because he's just going to get in the way. So here is my frictional vector. Alright, because obviously it's going to slow down, it's in the opposite to the direction of motion. So look, just to remind us, we know that the frictional vector is equal to, it's going to go in the opposite direction of motion, so it's going to be the normal times the coefficient of friction, and it's going to be in the I hat direction. So let's just apply this. We know that the normal vector is equal to the weight vector, which is equal to 60g, isn't it? Yeah, so 60g. It's in the negative direction, and its coefficient of friction is 1 over 3. So it's going to be equal to negative 20g in the I hat direction, equal to the frictional vector, like so. Alright, so what do we have next? Can we do anything else? Now you need to remember, of course, that we're not changing anything. We're only adding a frictional force in. So our j hat analysis, or our y analysis, y prime analysis is still correct. So the only thing we need to add in is our frictional force in the I hat direction. So let's just very explicitly write that the frictional force is equal to negative 20 in the I hat direction plus 0 in the j hat direction. So if we just apply finally Newton's second law in the y hat in the y direction, and that's going to be the mass times the acceleration in the y. No, that's incorrect. I'm talking about the I direction. Excuse me, just got a bit ahead of myself there. Alright, so we're nearly finished now. So what do we have? We still have 984 in the positive I. We have the weight vector, which was 80g in the I hat, and we have the frictional vector, which is 20 in the I, 20, wasn't it g, wasn't it? Yeah, 20g, excuse me, 20g in the I hat. That's equal to the mass, which was 100, times the acceleration. So let's just take out the calculator. So 80 multiplied by 9.81. We need to add to that 20 multiplied by 9.81. And we need to take all of that from 984 and divide it by 100. And we're going to get 0.03. So this time the acceleration vector is equal to 0.03 in the I hat direction plus 0 in the j hat direction. Alright. So yeah, that's all I've got to say about that. Thanks for watching. Please pass it on to your friends and subscribe to my channel.